Okay, and this case study should be also a pretty quick one, but this is a mine that we did a hyperspectral study at earlier this year. When we were putting together this class, John Layton from 3VG and Maddox informed me that he also had some Sentinel INSAR data for this area. And this presentation is about how you integrate INSAR data with other data sources. So the original project was to use hyperspectral scanning, some structure and geologic mapping, and both radar and LiDAR, and to integrate those data sources in a way to help with geotechnical characterization. And what we found in this study, it mainly focused on this upper part of the slope here, but we found an area that was moving with the radars, and we're able to correlate that with hyperspectral scanning that Isabel Barton conducted to swelling clays, specifically montmorillonites and some of the weaker igneous rocks. So now we have some Sentinel-1 INSAR data, and it has a little bit different time frame. So the project that we worked on was over the summer of 2019. This data set starts in October to January of 2020. But this is showing the INSAR data from Google Earth. And these are a down sampling of points to make it quick to render and easy to see. And in the areas that there is movement, they keep a higher point density to make it visualize quickly. And what we'll be talking about is this area here on the east wall of the mine, and that was the area of the study earlier this summer. And I'm going to show some dump movement here on this dump and the directional movement associated with that, which is quite logical and kind of a good example of directional movement analysis. So this east wall is what we'll be talking about mostly throughout the study, and the integration of the INSAR data with the ground-based synthetic aperture radar data. So here's the ground-based synthetic aperture radar data, and it's a subsampling data set. And so we're going to do a presentation in a few weeks on subsampling specifically. But what you should think of subsampling as is a technique applied to synthetic aperture radar to look at smaller rates and to help reduce atmospheric noise over time. And so this is from July to September, so a pretty long time frame to look at. And we're looking at a plot of cumulative displacement with a fairly low scale. So the scale goes from negative a quarter inch to positive a quarter inch. And the white lines on here are major structures or mapped faults in that area. And you can see, the movement, this larger moving block here is directly correlated to structure on the southern side of it. And it's correlated to lithology on this bottom side, which will show in other figures. So what this presentation is really about is how we integrated that data. And I just want to show how easy it is. It's not actually a very complicated process. So here's a video that was taken in Gem4D, which is currently an open source software. And these large squares are the Sentinel INSAR data. And the small squares that are on the surface behind those large squares, that is 200,000 points of synthetic aperture radar data. And what we're going to do is first, I'm going to step out of PowerPoint. We're going to go through a file in Google Earth. After we're done with that, we're going to talk through a file that's in Gem4D. We'll come back to PowerPoint and have some conclusions. So here we go. Okay, so now we're in Google Earth, and we're at an altitude of around 9,000 kilometers, looking at southwestern United States and northern Mexico. And we're going to zoom in here to a eye level that's approximate to the satellite orbit of Sentinel-1. And that's around 690 kilometers. So somewhere right in here. It's pretty close. And this would be the perspective of the satellite. And the satellites are side looking. And so the mine site, they've been awesome to work with through this case study, but they've kind of chosen to remain anonymous through the publication. So I'm just going to turn off the coordinates here, and then I'm going to fly to the actual mine site. So here's the mine that we were able to evaluate, and we're going to be mainly talking about the eastern wall of the mine, which is here. And in this analysis that was done by 3V Geomatics, there's actually 3 different satellite looks. So the ascending look here was at 35 degrees, and there's 2 descending looks, one at 30 degrees and one at 39 degrees. So that's the perspective of the 2 different radars that are looking at the slope. So if we look at the geometric distortion, these are the areas where the radar is not able to see, and that could be either because shadow or because of overlay. So if we zoom in on the mine, those areas are actually quite small in this case due to the orientation of the mine and the pit, but also some of the slope angles. So that's geometric distortion there. If we turn on surface disturbance, so this is usually temporary disturbance due to mining. There is mining in the pit bottom in this area. There's a pit lake that fluctuates over time, and that's causing a temporary surface disturbance or temporary incoherence. We can turn on the displacement points here, which might just take a second to turn on. So here's all the displacement points, and we'll be mainly talking about this east wall. But first, I want to talk about directional movement, and I'm going to do it on this dump here that's just slightly to the west of the mine. So I'm going to turn Google Earth so we're facing approximately north, pretty close to north. And I'm going to turn on the directional movement map. So right now, easterly movement would be red, westerly movement would be blue, and downward movement would be white. This is looking approximately north. And you can click through these points and see that the dump is settling in a very reasonable way, and a way that you would expect, with these slopes here that are facing to the east have a downward and eastward component. So we can click through a few points and look at that 2-dimensional vector in an up, down, and east-west plane. We can look at the other side, and it's going the opposite direction, down and west. And because this dump is quite symmetrical, so if we went right to the middle of it, the vector of movement should be down. And this is resolved basically by looking at both the ascending and descending data. So the ascending's blue and descending's green. So over on the east wall, where we were able to do ground-based radar, there's a little bit of shadow from one of the satellites. So that means we don't have overlapping coverage. So mainly in this east wall area, we have a lot of coverage from a single satellite. So the movement here is resolved in a downward direction. So if I turn off the directional movement, what we can do is look at these different points through this area. Basically, this is steady state movement. There's little to no acceleration in this area. This is an old historic wall that was mined almost a decade ago and hasn't had a recent mining. However, if we look at this movement area down here in the lower part of the slope, the movement is quite a different shape. So this would be progressive movement as it's just slightly accelerating over time. So viewing this in Google Earth is pretty easy, quick way to kind of click around and see what's going on. Another thing that's possible to do with INSAR data is to calculate the signal to noise ratios. And so what that is if there's some inherent noise that happens in INSAR monitoring, and that can be calculated, and the standard deviation of that noise can be calculated. So if you look at an area and you look at the standard deviation of the noise rate versus the movement rate, and you take a ratio of those, it will statistically show you where there's likely to be real movement. And so what these are contours of signal to noise ratios here, with 5 being the innermost contour. And they're a way with INSAR monitoring that you can identify very slow moving areas, even if it's below maybe even the accuracy of the radar, by looking at the data statistically. So we're going to show in later presentations how you can integrate that with other sources of monitoring data, ground-based monitoring data, to make sure that you're looking in the right spot. Yep, and this is just a quick way to look at it. I think we're going to now step over to Gem4D and talk about how we integrated the data there. Okay, so now we're in Gem4D, which is an open source software that was made by Frans Besson. And what we're showing is a detailed digital terrain model of the pit. We are looking at the east wall of that mine. And the colors represent 3 different geologic units. So you can see the different geologic units, and the black lines are the major mapped faults in the area. And what we did, we were able in QGIS, which is also an open source software, we were able to convert the INSAR data to the local mine grid coordinate. So we're now looking at the CSV that we imported. So it has an easting, northing, an elevation, and INSAR data. And I'll just show you just how we brought that in to the software. So just by loading a CSV, all we did here was just change the name, the data label, to INSAR in inches. So we brought it in and scaled it in a certain way to look at 2 inches of movement over that whole entire October to January timeframe. We were also able in the mapping tool to bring in 200,000 points of ground-based synthetic aperture radar data. And the mapping tool in Gem4D is mainly for mapping structures, but you can still bring in data that's associated with a X, Y, and Z position and skip the structural data columns and add an extra data column. And so that's what we did. We brought in 200,000 points of 12 hours subsampled radar data into the software. And so it's just loading really quick here. And here's the INSAR data. I'm sorry, the ground-based synthetic aperture radar data. I'm going to make it a little bit more transparent so that we don't lose sight of the INSAR data, but we can zoom in and see that obviously the spatial resolution of the pixels of the ground-based synthetic aperture radar data is a lot smaller than what you see from the Sentinel satellite and the downsampled number of points. But you can see that the regions of movement align generally, and they align on structure. And then here, they align on the lithologic contact here between the schist and the Pioneer formation. So one thing, the ground-based radar was looking at a fairly horizontal line of sight. The INSAR satellites are able to monitor this flat area above this moving area here. So you can also look at a histogram here of all the different ground-based points, and we can look at a histogram of the INSAR points, which they were all positive points here. There's no negative points in the absolute rate of what we're plotting. So it's just a really simple way to integrate it. Basically, if you can get your INSAR data or your ground-based data in just a format like we showed in the data format presentation of just X, Y, and Z and a column of data for whatever time frame you're looking at, there's nice free open source softwares that can easily visualize these data sets. Okay, so just wrapping this presentation up, what we showed is that data integration is becoming pretty easy with open source software. We didn't show the unit conversion from from geodetic coordinates to local coordinates because of the privacy of the mine, but that can be done in QGIS or it can be done in ArcGIS with just a little bit of training. And then the data can be visualized in GEM4D. There's also commercial softwares, MineSight and iSight and Leapfrog that can do similar data visualizations. And really the key step to these integrations is making sure the coordinate systems are the same. So converting between local and geodetic coordinate systems is extremely important. And once you do that, and you can go both ways with it, so you can bring your geology into Google Earth, or you can bring, say, your images in Google Earth into your radar software, the possibilities are almost endless of the integrations that can be completed. So if you just kind of focus on the middle step and figure out some speedy ways to do that, I'm sure you'll come up with some clever ways to cross-validate and compare data.